Okay, welcome back. Let's try to wrap up with this data set and move on to the second data set that we're going to look at, where we actually are going to address some of the data cleanup issues, where we can think about, are there any sort of bulk processes that we can apply to maybe clean up the data a little bit. So, but first we want to get this. There's one last step we need to do to get this into a state where we could export a report for MENA. And that is, we got to bring up the document grid. So view document grid. So everybody should have now trained a model and repicked all the peaks, which will give us Q values. And now we want to go to document grid. And I guess, let's see, if we're in the document grid, we should have this MStats input plus. We can take a quick look at that. Oh, that might be huge. That might have been a mistake. I guess that's actually a really big report. I think that was kind of a mistake. So let's switch to replicates. So I don't have enough. Okay, so what we need to do is we need to annotate the replicates in a way that MENA can tease out the sample one and replicate information. And so first we need to add those two annotations that we had. So let's go to settings, document settings, and we need to add bioreplicate and condition. And while we're here, let's go to reports and put MStats plus input report. So now I would say you should always do this if you're going to export a report from your document, add it to your document. So then if you give your document to somebody else could export that report. So yeah, especially when you publish your your data. So, whoa. Huh. I don't think I want to have, so I seem to have a condition that is healthy and diseased, which is not really what I'm doing here. Is that what everybody else got? Yeah, okay, so I don't know why that happened to me. Just lucky, I guess. I'm gonna edit the condition, and for me it's a value list, but I guess maybe other people, what we want is a text value. And it looks like I have to, okay, so everybody else is looking at this. Okay, so now I want to go back to the Bruder data set directory, the folder. If you don't have a Windows Explorer up for it, you can just go File, Open Containing Folder. And Skyline should start a Windows Explorer for you. And what we're interested in is this files.csv. So go ahead and open files.csv. Whoa. So here it is. And this is just a list of files with these annotations. So, and you can imagine that these are just sample annotations. There could be all kinds of sample annotations here, and you can bring them into Skyline the way we're going to bring these ones in. In this case, we just have sample, we have bioreplicate and condition, which are exactly the same. Let's go ahead and select them all. This is the way Mina said she wanted things annotated. I contacted her and said, okay, I'm going to give you some reports. How should I set the bioreplicate condition of these things? And this is what she told me. So Control C to copy, and then switch back to Skyline, and then just click on this upper left-hand corner under bioreplicate. And you want to, at this point, there's one little thing is you want to make sure that you have a full blue rectangle and you don't have a a blinking cursor. Okay, big difference. So you want to have a full, if you do have a blinking cursor, you can just press escape and you'll get the blue rectangle. And then just Control V to paste. And that should fill all those values in. And that's it. So now we've just annotated those, and we would go to export a report from Mina, and here's how we do it. Go File, Export, Report, and MS Stats Input Plus, and then with Mina, and a lot of people working in R would prefer that you do invariant format. And that's going to give you periods for decimal points. It's going to give you always English names. So even if you're in China or Japan, where you would see localized UI, you'd still get English names. You'd get the replicate and sample type, and you get all the names in English. And that means that when you import it into R, your variable names. So invariant gives you just sort of the most. Especially when you're intending to talk to other tools, it'll give you the most consistent format. So if you're exporting a report for yourself or your friends and you want it in your language, then you would stick with whatever language was here. And if you're in Europe, you'd get your localized decimal separators and everything. But if you want to work with another tool and you're not sure, or you know that the tool can only deal with US English number formats and titles, then you do invariant. And so then we would click export and tell it where to export it. And we could say MS Stats Plus, name it Bruder. Right, Bruder MS Stats Input Plus.csv, right in our folder, and click save. And then Skyline's going to put something up and say building report, and this is a case where I know that I just do not have the memory to get this report exported, so I'm actually just going to cancel. So that's it. But that would be the report that we're going to use. I have a saved version that we're actually going to use. So go ahead and close the document grid, file, save. That in itself might take a little while for Skyline to save this entire document. But that's it. We're done with Bruder, and we're going to move on to the Selevsek dataset. So let's start talking about the Selevsek dataset. All right, so the Selevsek dataset is another dataset coming out of Eversolid Lab, partnering with the Biognosis team. Biognosis comes out of the Eversolid Lab. The founders of Biognosis were actually in the Eversolid Lab when I first met them. And so it's another one of these very similar experiments where collect a library using DDA and then run DIA samples and quantify the peptides based on that. And in this case, again, pooling the sample, this case they did fractionation. So the last time we saw it, it was 24 runs on the same sample. In this case, there's actually 42, I think, 42 runs that they built the library out of, but they did deep fractionation and they really tried to get it, they were trying to build not a sample-specific library, but a proteome-wide library. So they did it for yeast. So similar to the pan-human library that came out of the Eversolid Lab that we've been talking about a lot. This is like the pan-yeast library. So I read the paper and pulled out a few things about the methods in the library, and then the end result again was an assay library. So which is basically a massive transition list with relative ion abundances for the fraction. That's the spectral library part, and then IRTs, so normalized retention times. So here I pulled out a few sentences from the methods that I think are particularly important. One is that they did their search with semi-triptych digest. Who knows what a semi-triptych digest is? Hear from somebody new. What's a semi-triptych? What does that mean? Yeah. So basically, we've been working with fully triptych peptides. A semi-triptych means like, well, one of the ends has to be triptych, and then the other thing can be anywhere it wants, right? And it turns out if you look at these search results, about 20% of the peptides in the search results are not fully triptychally cleaved. So that's right up there. We have a library that includes these semi-triptych things, and we have to decide: do we want to allow them into our quantification? And since we're already struggling with memory here, we're not gonna use them in our quantification. But I've run these at home on bigger machines with the full semi-triptych, and in order to, if you read the paper, it'll say our library includes this many peptides. And when I first did the analysis, I just imported it into Skyline with normal trypsin. I was like, well, I got 20% less than they have. And so it took me a while to figure out how to get up to the numbers that they were reporting. And that's partly because there's, these semi-triptych peptides, which Ludovic Gillet, who's the guy at the Aerosol Lab who created the library, is, pretty emphatic that, well, those really are in the sample. Whether or not they're all that usable for quantification, I don't know. So then we're allowing two miscleavages that might come in useful: carbamide methylation and oxidized, carbamide methylation of cysteine, oxidation of methionine. I didn't highlight the methionine. So those are the two modifications they allowed. They searched with sequest and mascot, got a PepXML that they got a combined score using iProfit. Just some information to know. Then I was like, this seems kind of suspect, and we were talking about it. Some of us were talking about it yesterday. They chose an iProfit cutoff score of 0.0242. What kind of probability is an iProfit score? Does anybody know? It's a posterior error probability. So that's not a Q value or a P value. That is saying that they went all the way to taking spectra where the chance of correctness is 2%, 2.5%. So if I take 100 spectra that have been matched with this score, 97.5% of them are going to be false discoveries. And that they say is what they needed to get 1% false discovery rate, but 1% false discovery rate at the PSM level. And so PSM level is is the most permissive level, and especially when I have 46 runs. So like the things that I'm finding, even with fractionation, I'll probably find them multiple times in multiple runs. This is kind of, to me, is like, well, why would I want to do that other than I really want to report the biggest list possible? So when I built this, and the library I built, I started with this 0.2, but then I quickly switched to my normal cutoff for peptide profit, or these profits, is 0.9 or 0.95, and we'll see how that impacts things. Yeah. Yeah.
They still want reviewers that undertake things or results or but the main goal is like we want to do a large research.
Yeah, I mean it was a large set paper, and I mean they did other things. I mean I don't know, like it's a really great data set. It's been incredibly valuable to the field and to us. So for what it, I mean, if they were trying to report something clinically, no way. Like, show me the SRM study, like show me the targeted study. But in terms of they were just trying to prove the concept of, hey, we can create, a proteome-wide library, a big library. So basically, there's one paper. The first paper I showed you is kind of like, hey, we do DDA on the same sample. We don't even fractionate, and then we run it again, and you saw the impact of that. There was like really low false discovery rate. Hey, I can find the same things I find in DDA. I can find them in DIA. So if I just generate a library on my sample, I can go back and interrogate my sample, and I can get better quantitative results. That was kind of a path-breaking paper. And then this is the first paper I know of that said, well, we can also do all kinds of crazy fractionation, create a bigger library. Now we'll do single shot DIA. We don't expect to find everything in there. And I think if you had been a reviewer and you said, well, that's really permissive, they would just say, they probably would have just responded. And that's one of the things we're going to kind of analyze is well, those things will fall out in the false discoveries, so they're in the library. They may not be the greatest, but you probably won't find them either. So it's just a library, and now you have to prove that stuff's in your DIA, and I think that's a little bit too cavalier, but anyway, so they weren't making like real scientific conclusions. So definitely very valuable paper, sort of like as with most things, the first thing that gets done turns out not to be perfect. We don't use the old swath method anymore. The instruments are getting better. But still, good to be aware of. Another thing that like, especially if you're going back to old data and you're deciding, well, can I just use this method? My answer was no. And part of it also was they said, oh, we chose the 3 to 4 most intense ions, and that's what they use. That's their assay library. It's just 3 to 4 ions, and that results in 83,000 precursors. And that's including the 20,000 or so that are semi-tryptic, and certainly quite a lot more because they allowed methionine oxidation. Because you get both the methionine and the oxidized form show up a lot. So it kind of doubles your numbers in anything that contains methionine. And then this number of transitions, which, even, 3 to 4, but it's like, well, okay, that's 4 times the number of that's too low. So, and again, with an assay library, you can't go back because we don't have the original spectra with an assay library. And so my feeling was like, okay, I need the original data. And I went and they just had the pepXML file. I had to contact them to get. I got both the MZXML files and the FASTA file. So, basic concept of Skyline is that we came up with this idea of targeted method refinement. So when you're going to target something, you can start with a really broad method based on your spectral libraries, your RT prediction, unrefined methods, which is what I would consider these big proteome-wide things. Any other sort of previous measurement information, you put it in here, do this targeted method refinement, and eventually your goal, especially if you're this used to say clinical assay, if you're going to something that's like clinically measurable, you're going to have to do lots of refinement from this top level of DIA that we're talking about to get down to a fully quantitative assay, and we talk about using Skyline to travel around this multiple times, and I'm going to show you that even in this hugely broad DIA, I came up with a refinement that I think will give us better quantitative statistics. So basically, you build a method, run your method, evaluate the results, and refine. And in the case of DIA, you maybe don't even have to run the method. You don't even have to keep running the method. You can go around this without rewriting the method. Although in this case, we do have 2 different data sets required to do the refinement. So things that could happen in this refinement block, we could be looking for abundance, measurability, differentiation, degradation, digestion problems, like not all peptides digest the same. repeatability, quantifiability, like that's what Mike was talking about, that Lindsay Pino in our lab is doing, is actually doing figures of merit on every detectable peptide in yeast. And then we might use retention time knowledge to do scheduling, and we might be doing collision energy optimization and optimization of other parameters as we go into more targeted stuff. So that's that. Now I'm going to show you how at a, so we talk about this a lot when we're actually doing courses where we're trying to produce quantitative assays. Here we have a differential assay, but we can probably get better on the differential results by thinking about what kind of refinement we could actually do. So we're gonna use this Selevsek data to try a refinement. They just happened to collect data in a way that gave us an opportunity to do a refinement that we were starting to do in the MacLean lab. So we're starting to explore how can we get better quantitative numbers across a whole proteome, and that's what Lindsay's graduate work has been focused on, actually doing calibration across the whole proteome. So let's, I think I'm gonna just close down this skyline here and start up a new skyline, and we're gonna go over oh yeah, so we're gonna go over we're gonna build a completely new document again. So go ahead and click blank document. And so this is the first part of the getting your settings and your targets ready to import your data. So this is the first part of our workflow, and we're going to be using somebody else's data, but we still have to do this. So we're not going to actually build a library. You've been through building a library. If you came this morning, we built one from the MacLean results. You built one with the inspect.xml, is that what it was called? In the tutorial, you built a library, right? So we could, if I wanted to build a library, let's go to settings, peptide settings, and you won't all be able. So here's my group. Oh, that's the tutorial one. That's the assay one built from the assay library. But if I wanted to build a library, I would click build here, and I would call it Selevsek 2015, and maybe I would put it in the Selevsek 2015 folder. And here you see Selevsek yeast. So here are some things. Here are two libraries that are already created, and I'm going to say, well, let's say I'm going to create one at 9.5. So yeah, I guess I'm calling this Selevsek yeast 9.5.blib save. So again, I get the choice of do I want to keep the redundant or not. I guess I'll keep it, and I'm going to say 0.95, and I'm not going to include ambiguous. And this has the IRTs in it again. So this is how I would set that up. Very similar to, you've done this once in the tutorial, and again this morning if you were here for Bruder with MaxQuant, I would click next. And now here's where we don't have enough. I'll show you the files, and you'll see why we couldn't all do this. So on the Samsung, I have this. If you want to do this at home, you can come and get this from me, but let's see how big it is. If I go into 2015, oops, that's Bruder. If I go into Selevsek 2015, I've got this DDA folder, and here I have an iProfit combined XML, which is 2 gigabytes. So big, and then I have I think 42 or 46. Let's see. I have these 46 MZXML files, which are fractionated. And then there's fractionation, and because it's an osmotic shock experiment, they've actually like done searches on samples that are all the various, time points in their osmotic shock. So somebody was just asking about pooling sample. You can also run DDA if you have if you have an experiment in mind and it's gonna be say healthy and diseased, you could either pool everything, or you could actually run DDA on both pooled healthy and pooled diseased. Or if it's going to be a time course, you could run either the entire time course pooled, or you could run separate each time, which is sort of what they did. So this is this fractionated thing, hoping to give them a really wide widest possible set of things that they have seen that they are willing to look for in DIA. But you can see, let's see, what does it say? Yeah, so this itself, if I were trying to give this to you, it'd be 50 gigabytes. So if you have 50 gigabytes extra, you want to take it home, I can give you these data, but it would have required an extra flash drive, and some people wouldn't have the space. So and then I can just go and add files, and we'll see if it's even looks like it would go quickly enough for me to go through. But you can't follow along with this. So if I go to this Selevsek DDA folder, here's the iProfit pepXML, and I would click open and finish. And it's going to start building, and it goes through, and first it loads each file individually, and then it pulls the spectra from it. And we know from experience that it's also going to have to do a filtering step. I bet this is, yeah, so this probably would take a pretty long time. So I'll leave that running, and we'll see how long it takes. I'm going to start a new instance of Skyline. But that's it. I mean, eventually it will end and I'll have a library. So we're now going to pull the pre-built library, which is what I put on the flash drives, and we're going to set up the method. So everybody switch to default, settings default, so we all start at the same place. Do not save your current settings. Okay, so first thing we do is turn on integrate all, because we're doing that kind of experiment again. And then we'll go to peptide settings and digestion trypsin. If we wanted to do the broadest possible set of targets, we would choose trypsin semi. Right, that's how we get as close as possible, that 85,000 number that we saw in the manuscript. But we're going to just stick with fully tryptic. That's our first refinement, or sort of limiting of the data. But we will allow the two miscleavages that they said they allowed. The other thing is we'll go ahead and add a background proteome. So click add, and we'll call this yeast FR. So this is, well, let's take a quick look at the FASTA file that we have for these data. So Selevsek, and I had to request this because so this is a forward and reversed. So they used some algorithm to reverse all the peptides. So this is what they actually searched. They used Sequest and Mascot to search this FASTA file. And it was, if you read the paper, it's reported as being the February 3rd, 2011 SGD FASTA file. Great. okay, I went and found that, and then there's like actually 4 different variants that are possible, and things didn't quite match up. And then I realized, well, I'm not even sure what reverse they use. I would like to be able to reproduce exactly the peptides that they were searching against, and so there are several different reversing algorithms. I mean, there's the simplest one is just reverse the whole protein, but then they also do like reverse peptide sequences where you keep the cleavage points all the same, but you just reverse the peptides in place. And I think that's what they did. But anyway, so the best thing to do, they had not put this up on their drop point, is to go back to the author and say, hey, give me your FASTA file. And here you can see that they did, here's YAL01C, and then there's reverse underscore YAL01C. And it goes all the way through there with every protein and every reverse protein. So that's what it looks like. So we're just going to open one that I already built. Click open. And this is yeast ProteDB. Oh, no, don't do that. That's the wrong yeast ProteDB. I don't know how many people showed up in there. We want to go into DIA pub Selevsek and then yeast Selevsek yeast FR ProteDB. That's what we want. Click open. So these can be valuable resources you can share. Here's a question I have for everybody. Well, so what do you make of the number of proteins? What do you expect of the number of proteins? What? Yeah, that's more proteins than yeast has, but oh, whoops, wait, we're expecting reverses in there. So it should be twice as many. So, what? Exactly, yeah, what's the 3? And so, yeah, I don't know. So I went and opened it, and everything's getting doubled at the beginning, so I went, oh, let's look at the end. And I couldn't see anything immediately at the end either. Yeah, I mean, so maybe there are contaminants in here. I think the IRTs are also in here. Not positive though, maybe not. No, I mean, they have to be finding the IRTs, so there must be IRTs in here. Okay, so anyway, that's it. We've got our background proteome. That's what they actually searched. Prediction. So again, I have an IRT calculator. This is an IRT calculator that I think I did some work on. This might actually even be times from peak apexes. I'm not positive, but so we're gonna go ahead and add the IRT. Oh, whoops, no, we're gonna click on the calculator button and click add. And then we're gonna open one. And we gotta get to that yeast Selevsek folder again. And here's this. This is what an IRT calculator looks like when it's not inside the blib file. It's called IRTDB. And you can see that I did it. It's recreated with 0.2. So this is as permissive, I think, I think this is an IRT calculator that's as permissive as you get it's got semi-tryptic cleavage in there, and it was just my attempt to get IRTs for everything that was actually used in the Selevsek paper. So click open. And there you go. So there's 82,553, which is close to what was reported. What was reported? 83,500. So yeah, so I'm even still missing some things. And these are the biognosis, and it looks like these are actually the true biognosis values, not recalibrated. So we have 100 and 0 and minus 27.4, so I didn't recalibrate them. But so let's call this Selevsek yeast IRT calculator. Click OK. And we'll go ahead and say 10 here, even though it's not important, because we're going for 10-minute window extraction. On the filter tab, we're going for, here we're going to go 7 to 45 and use 0. And this again gets me as close as possible to what was used in the paper. So last time we allowed 6s. Now this time we're a little bit more restrictive, but not hugely more. And we don't go up to 20. We don't go up to 55. So on our library, we got to add a library. And now we're just going to go edit list, add. Is everybody with me? Am I going too fast? No, okay. So browse. And yeah, we keep ending up in Bruder. And so we're building this yeast 95 redundant.blib, but we want the 90. So I was a little bit more permissive. I used 0.9, which we think should give us less than 1% FDR at the PSM level. But we're not interested in the PSM level. We're interested in like the peptide and protein level. So we're going to be assessing that soon. So click open. And then we'll name this Selevsek yeast also. Okay. Okay. And then we have to check it. Everybody got that? Okay. Modifications. Carbamide and methylcysteine. And oxidation M. We're gonna allow that just like the. So in this is our first, so we're gonna actually do 2 experiments. We're gonna search the data the way they were searched in the paper, except that we're changing our targets to use more fragment ions, and we're not going to use semi-tryptic cleavage, and so we're a little bit narrower, but we're still going to be doing a really pretty broad search, and then we're going to do a refined search where we're trying to get more precise numbers. So so that's it. We're not doing quantification, not doing calibrated quantification. So that's it for peptide settings. Click OK. And now it says, hey, you don't have IRTs, and we can say, oh, we'll take as many as 6 transitions for our IRTs also, but it's going to add the IRTs to our document for us, and there they are. And now we want to do transition settings. And we come up with full scan selected. If you don't have full scan selected, go ahead and select it. And we are going to use, we're going to use DIA as our acquisition method. On these, we're going to use TOF. We're going to use TOF profile extraction, and we're going to go 18,000. Yeah. Yeah, so this should be matching how you acquire your data. Yeah. So this is just helping Skyline to calculate the width to extract things from, and even if you collected, so yeah, on the first day, I guess I've got it here. Yeah, even if I collected at some resolving power, you can use whatever resolving power you want, and it has a big impact, right? This was my resolving power experiment for this paper, where we used the default at the time was 10,000, and then we later found, hey, actually, like 60,000 is really a good level for this. So, and the impact is, we had 10,000, we were extracting this much. This is a 10,000 window. So your resolving power, the higher it is, the narrower this window is. So you can do, actually, Jake Jaffe was one of the first people I knew who started doing experiments on this over at the Broad Institute, and he called it ultra resing, which meant that even though he collected at a certain resolution, he would narrow so he maybe collected at a resolving power of 20,000, but he used 60,000 and just take a narrower swath. So you don't have to. We try to make the translation pretty natural, but you don't have to use what you could say, I want, if you had a mass error problem, like you had mass shifting or something, you might go like, well, okay, I collected at 18,000, but I got to go 12,000 because I have some mass error issues. Or you could say, well, I want to go with 35,000, and that just, the larger the number, the narrower the extraction, and the smaller the number, the wider the extraction. So we're going to use 18. We're also going to use high selectivity extraction. That means, hey, it's a cell lysate. We really want to try to narrow that window a little bit. Yeah. No, we're summing. We're summing. Yeah. Yeah, you lose intensity. It turns out that ends up being better. Even with lost intensity, that ends up being better than a wider window. So Mike and I really expected this to be sort of the best window, which is now you lose very little intensity. This is about twice what the resolving power should. The resolution is the full width at half max. So this is twice the full width at half max. You get most of the peak, but it turned out that we got too much interference that way. And so this ended up being better, and even better in certainly always with the Orbitrap, we've found that centroiding is giving us better data. So, because once we centroid, then we can do very narrow windows. Yeah. Yeah. No, actually, because a lot of we had that problem with SciX until recently, and they helped us change it. But you get fairly similar values. This looks really, this is the SciX data, and you can see the values change radically from 500 to, if you think about this is 14,000, and then summed would be, so it'd be quite a different number. And they have since worked with us to try to get the numbers to match better. Oh, I didn't start to record. Yeah. Okay. Well, no, I did. It's just recording it. Yeah. So yeah. Nat will just cut that out for us. See what. Okay. So yeah. So we're extracting. Centroiding. Sometimes the number is different, but most of the instrument vendors are they're either using an area number or a sum number that's very similar. So the centroid will still represent the total number ions per second entering the detector. Okay, so we want to keep going here. Now we got to do the isolation scheme. So go ahead, and we're going to add a totally new isolation scheme here. And we'll call it Selevsek 2015 32. It's a 30 or 32W, 32 windows. So ideally, what I'd love to do is just click pre-specified and import, but I did not put a WIF file on this for you. I realized that again last night. Like I had to do this last year, and I was like, but I forgot to update the flash drive. So I'm going to show you what we did last year to get the isolation scheme. It's pretty easy. But what you'd really prefer, if you have pre-collected data, you really want to import the isolation scheme from the data. But we're going to calculate it, and I'm pretty sure we can get it right. So click. So you want to type 400 to 1200. Whoops, sorry. 399 to 1200. And our window width is going to be 26. So that's the measurement windows. Those are the windows that actually are measured by the mass spectrometer. And then we want to have a margin width of 0.5. And that's basically the method that they did. So if I have 0.5, I think if I switch to extraction width, oh, it didn't. So at this point, you see that these are 26 that are going to be measured in the mass spectrometer, but they're actually 25 width windows that we're going to do extraction from because we're putting margins on them. So click OK, and that will fill that in. The one difference is that they actually measured for this first one. So click on the first one here and type 400 and then enter. So they do 25 MZ for the first one and then 26 MZ for everyone after it. That's what they actually had, yeah. Yeah, don't. Yeah, that's where you shift it to a dead zone. So you have the ability to choose optimized window placement, which is what gets done in the MacLean lab a lot, especially because it's important to the overlap, the demultiplexing. But if you're using margins, so yeah, there's like, this is more the Aebersold lab way, wider windows with margins, no overlap, and now we're seeing, variable window and everything. And the MacLean lab way is dead zones with demultiplexing, and but this is Aebersold lab data. So click OK. And then we're going to use our IRTs and our retention time prediction and 5-minute window, 5 minutes on either side, which is going to give us a 10-minute window, right? On the instrument, we're gonna go 50 to 2000. And then library, we're going to go 0.05. Another thing that I got from reading the method, that's what they used. And we're going to have 6 transitions and a minimum of 6 transitions. Oops, we got to come back to this. I did it in the wrong order. But anyway, we'll come back to this because now something we do in the filter tab is going to change things. So switch to filter, and we're going to do 2, 3, and 4. Not quite as permissive as last time, and just 1 and 2 transitions, and Y and B. And then we're going to say ion 3 to last ion and turn that off. These are pretty common settings for MacLean lab. They probably would maybe not go up to charge 4. But this ion 3 to last ion, what's the other way to get rid of your ion 1 and ion 2? well, going directly into it, but the setting that we used last time was, if we go to instrument, we could also set this up to 300 or something. So, but that's, and so now we have to go back here, and for some reason this got reset to 3, so you got to switch it to 6. I have to figure out what exactly changed that, and then we're going to use from filtered product ions. So once you get done with your filtering, go back. Anybody need a review? Should we review those? Okay. Filter 23412 YB ion 3 last ion and no special ions. Does everybody look like that? Library 0.05 match tolerance 6 and from filtered product ions. Instrument 50 to 2000, and then the full scan settings 18,000 high selectivity plus or minus 5. Okay? So now we're going to just import that FASTA file. The whole FASTA file, right? We're trying to do a full proteome search. So this is not a restricted set of proteins. This is file import FASTA. And we've got to get up to this, to our documents folder and into Selevsek 2015, where we find the FASTA file down at the bottom, this SGD 03 Feb 11 2011 reverse. Everybody make it there? I lost people? Good, okay. Click open. And that will take a little bit of time too. Not quite as much time as if we allowed for semi-triptych, but now it's got to get through all, it's going to read all those proteins and digest them and figure out which ones have spectra in our spectral library and get them all set up. Anybody have questions at this point? Yeah. We do have a wizard, so you can actually, you can walk through a wizard that will allow you to do this. Yeah, I wonder if the DIA wizard is good enough at this point. So yeah, we've been blowing right by it, but when you start Skyline, so one good way to start is this import DIA peptide search. And so this will actually take you through a set of steps that have you build a library. So here's the, you know, this is the search cutoff, you know, we would go 0.9, you know, so this, we've been jumping into a few things because I've got some stuff pre-built and everything, but yeah, this would take you through all the steps to build a library and stuff like that. So that's one thing, and then there's certainly tutorials that you can walk through and relearn all the steps. There's 2 webinars on this, so you can come back and follow these recordings, but there's also more recorded webinars. Yeah, but basically, I mean, the steps that, at the very high level, it's get your settings right, import your, the things you want to target and make sure that you have all your targets set up. Generate decoys, import your data. I mean, it's so that at the very highest level, right? This is the schematic we're doing. Is we're creating the spectral library. We've got acquired DIA data. We pick our targets, do chromatogram extraction, build an M-profit model, and peak pick on it, and then export a report. So that's part of why this workflow is here. Okay, so what is Skyline telling me here? How is anybody else at this point? There must be some people who are already past this point, right? No? How far are you? What percentage? 20%. Oh wow! You gotta get a faster computer. Yeah, that's the nice thing about doing these at ETH. We had virtual machines, so everybody was actually on the same speed machine. Made things really nice. And then the other thing is that typically a lot of the teaching we teach on really small SRM data sets, because you can learn a lot about Skyline just working on SRM data sets, and then there's never any processing speed issues. But we are trying to teach you bigger stuff, which mostly we would recommend you do on a dedicated desktop computer with at least 16 gigabytes of RAM. But all right, so yes, do you have a question? So we 8,871 proteins had no peptides, and so it's saying it's going to just discard them rather than putting a whole bunch of extra proteins into your document, which would slow things down. We're just going to not include them. And a lot of those are reverse peptides, right? So probably 6,500 or so are reversed. So click OK. And there they all are. And you can see that even up right at the top, you can see that there's something found in this reverse peptide. And for the most part, it's going to be just one peptide in any reverse protein. So the first thing we're going to do is edit, refine, sort proteins by name. And now that groups all the reverse underscore proteins together. And we get some above it, so let's move those down. So click on this Q004. How many people are still with me? Actually, who's not with me? Okay, a few people. All right. Well, so we're getting pressed for time, so we're gonna have to forge on. So click on Q004, hold down your shift key and click on this other one below there, the R004. So you get all of the target proteins down to the first reverse one, except for the IRTs. And then Control X to cut. And then page down once, twice, 3 times. That's what it took for me. And then move your selection up to the first protein after reverse. And Control V to paste those back in there, so that we now have the IRTs at the very top and all the reverse proteins above that. Does everybody have that? Okay, so let's do FDR estimation by decoy counting. All right, so who can tell me what they think the false? How would I know the false discovery rate at the unique peptide level? Well, actually the status bar is pretty close to giving me the equation. 148 divided by 44,679. So, nice feature of Windows 10 is I can just type that in, 148 divided by 44679. And so at a unique peptide level, it's a 0.3%. Right? So less than 1%. That should make us happy. When we got rid of, we were a little bit more restrictive than the paper, right? I think the paper actually, if you did everything the paper said, you would have an over 1%, I believe is like a 2% false discovery rate at the unique peptide level. And then let's do what it is at the protein level, 135 divided by 4,514. And so that's about 3%, right? But there's one caveat here, is that because I've got so much of the proteome, at the protein level, even when I have false discoveries in peptides, a lot of them are probably hitting proteins that I actually have in my sample. Whereas in the reverse case, whenever I have a false discovery, I'm probably hitting a new protein. So what I think actually is that the true protein false discovery rate is probably something like a third of that. So it's pretty close to 1% protein false discovery rate. That's my belief. But anyway, we probably can live with a 3% false discovery rate also, because we're, because, so you imagine if only 1% of 4,500 proteins is wrong, then what's that? That's like 40 or what now? Yeah, so 40. So that means that really the bulk of 4,000 proteins are true. And I only have 6,500 proteins. So that means 2/3 of my target proteins were detectable, right? And so now if I take my peptides, so really if you look at it, it's like 148 peptides, 135 proteins. So it's one peptide per protein. So now if you just take those and sort of shotgun them at the targets, 2/3 of the time you're going to hit a protein that we have other peptides for. So whereas we really basically have no reverse, that like everything in the reverse case is a one hit, right? And we have nothing else to hit. So every time we find a false discovery in the reverse case, it's a new protein, right? Every time we find a false discovery in the target case, well, 2/3 of the time it's a new protein, right? Because there's so many proteins that we know are already there by other peptides. So that's why I'm saying that, probably our estimation just by counting is not totally accurate. Yep. Okay, so now we have a document. What's the last thing we need to do to this document? Yeah. Oh, no, there's more things we need to do this time. Okay, sorry, what? Yes, go ahead. Does somebody you have a question? Okay, so, yeah, so another thing we need to do is remove duplication. So let's go to Edit, Refine, Advanced. And we want minimum peptides per protein. Well, let's just say 1. Any protein that's got 1. We could here, if we said 2, we would get rid of most of those reverse hits. But we're going to be more permissive. We say 1, and then we also want to remove duplicate peptides. And that's all we need to do in this refinement. So we want proteotypic peptides. We want only peptides that appear in one protein. So click OK. And that got rid of a couple hundred proteins. But I think a lot of peptides. So we got rid of thousands of peptides because they're not unique, and we're really only because we're going to do protein comparisons. We want ones that are unique. Yep. So edit, refine, advanced, and then you just go one peptide per protein and remove duplicate peptides. And I will now do the 2, but don't everybody else do this. So if I'll remove duplicate. So just 2. So all I need is everybody get through that first thing, and I'm going to try. We'll see what it looks like if we say 2. We're going to require 2 peptides per protein, which, in another experiment, me and I found that to be really useful, because then you have to have at least two peptides kind of in agreement that the protein is changing. So otherwise, you're really trusting this one peptide to speak for the protein, and little things can make you go wrong. So statistically, this is a safer bet, but we also lose another 500 proteins. We're down to like just one reverse peptide. So basically, our false discovery rate here is great at a protein level. Like we have really high confidence that the proteins that we were targeting are in there, but this may be too restrictive. So I'm going to Control Z again to undo that. And then the last thing I really want you to do is we're going to add decoys. And adding decoys is something that you really want to save to the end, right before you're going to import data, because Skyline doesn't try to keep your decoys in sync with your document. So if you're editing and messing around with your document, your decoys can get out of sync. So we go edit, refine, add decoy peptides. And here it's actually, we do not want to have reverse sequence decoys, because those will start to, produce the same thing as our reverse peptides. So shuffle sequence decoys is a better choice here. And we want 39,200 is going to end up giving us the same number. 202 is, so the minus 11 is for the diagnosis standards. So just click OK. That'll add the decoys. And if I look down at the bottom, it'll put them down at the bottom, and there they are. I'm going to press home to get back to the top, and then click this little disk to save. Oh wow, I haven't saved at all. We'll call this tutorial Selevsek, and click save. All right, so now we're going to, so that's it. We would import data now, right? But we don't have any data. So we're going to magically open a file that should be just this exactly with data imported. So file open. And we're going to do, we're actually going to go to Selevsek reps and open that. So in the beautiful thing about the Selevsek experiment is they actually did 2 experiments. They did this osmotic shock thing where they're expecting proteins to change. And then they did these replicates where they were just trying to prove that they could measure things stably with low CVs. And here again, on reading and exploring the manuscript, I think there's a little bit of smoke and mirrors in that they report 4 replicates for that experiment, but they actually collected 8. And when I asked them, well, why did you report your CVs with only 4 replicates? The answer was, well, that's fairly typical in the field. And it is, we do report CVs against, I see CVs reported against 3 things. But if you have 8, they collected 8 reps. So I'm going to use all 8 reps and just know that if people are reporting CVs on very small numbers of things, that's going to systematically underreport the true variance. The other thing is that if you choose, you also want to ask the question of how close together were these things measured, because if you do 3 replicates that were measured boom, 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 then that really understates your variance. Whereas if somebody's giving you 3 replicates, like with the Bruder data set, when we look at those 3 replicates from the 3 randomized cycles, they can be pretty far apart. And so their CVs, if they get really low CVs, that's more impressive than 3 replicates measured right next to each other. So we're one of the first things we do when we open up this file is we'll have a look at when these replicates were collected and how far apart they were. So there are the data. Here we got our IRTs selected again, and we can see the retention times look really nice. Peak areas look better than the Bruder data set. There's not as much variance in the IRT. It's not straight lines across, but it's not quite as strange. We can right-click and order by. I'm already ordered by acquired time, but you can see that the acquired time and the document are the same order now. And so let's go ahead and let's create a report that will show us the actual acquired times for all the documents. So view, document grid. We've got our replicates should come up. This document grid is incredibly powerful, and I would recommend that if you're going to work with Skyline much, you should learn how to use it well. But we're going to do a very simple use right here. You can just customize the view. So we have this thing that says replicate sample type analyte concentration. That's what we're showing. And we're going to create one that says that we're going to call replicate file times. And as long as I'm here, I'm going to point you to these little buttons up here. There is this little toolbar at the top that people often miss. There's a binoculars where I can find anything. So if I've heard about a value that I want to find, or I'm, let's see. I hear that there's stuff about collision energy. I can just type colli and then find and jump, and I'll find a collision energy thing. So definitely, and then there's also this question mark, which will give you the full documentation for all of the values. And then once I start editing, I have undo and redo within this thing. So I'm gonna close back up this proteins, and we're gonna focus on replicates. I'm gonna turn off sample type and analyte concentration. I'm gonna go ahead and put replicate name in there, and I want the file name and the acquired time. And you can see there's also lots of other interesting things. Actually, I'm going to go ahead and put this result file locator in there too. Oh, I don't want that. No, I want the replicate locator. Okay, so does everybody have that? Okay. Yeah. Yeah.
What's the little hashtag?
Oh, the hashtag means it's a number, and AB means it's text, and blank means it's something else. Yeah. Anyway, so all right, so click OK, and there we go. So this replicate locator is actually just a way of looking up the thing. But what we're really interested in is the acquired time. You'll notice that the replicate name is editable, so I can actually rename things here. So I could rename, 1 to 1A. Click enter, and you can see that it just changes everywhere, and I can undo that. So the acquired time. How far apart were these measured? So we start at 2:05 a.m. and we end at 9:35 a.m. So yeah, a little bit over a day, a little bit over 24 hours. So that's not bad. The MacLean lab frequently we do an experiment where we try to measure peptides 48 hours apart or 72 hours apart. Why would we do that? Yeah, degradation effects. So that was one of the things that I said I could do in my in refinement. Was degradation. So the nice thing about measuring a day apart is that peptides that are degrading are going to produce higher CVs, right? So I feel pretty good about that. But if somebody told me, yeah, I did my CVs, based on these first 3 replicates, which are measured in less than 12 hours apart, maybe that's not as useful. Okay, so now let's go ahead and look at the CVs. I showed you before, I showed you my R scripts that showed the CVs, and I thought that was so useful that I wanted to get it into Skyline. So we can go to peak areas, and we have 2 histograms. Basically, those 2 histogram plots that I showed you in my R-generated code, I then had an intern implement them over the summer, and you can get either. Let's take a look at the CV 2D histogram quickly. I'm going to pull this out and make it bigger. So there, let me see. Maybe if I also use log scale, that usually makes things a little bit. All right, so what do we know about the CVs? Well, there's a really nice concentration below. This line is 20%. There's a nice concentration, but we also see this effect of as we get, this is the log mean area. So as we get to lower, smaller peaks, our CVs get worse, and that's what we expect to. So. And we're already normalizing to medians. What happens if we don't normalize to medians? In this case, it gets a little bit worse, but not much. Okay, so now let's look at it in 1D. So view peak areas CV histogram. Whoops. I'm going to pull this out and put it here. Okay, so now what can people tell me? Wow, only 50% of our analytes have below 20% CV. If I normalize by medians, then it gets a little bit better, but not much. Okay, so what else do people see about this? Nobody has any observations about this thing? What's this thing? Why do I have this, other thing? And then, so this doesn't just look like one distribution, right? Well, whoa, am I including the decoys? Oh, it's the targets. Well, what do the decoys look like? Oh, the decoys look much worse, so that's great. That's what we're hoping for. But actually, let's zoom in on this a little bit more by clicking right-click and click properties, and then we can say a maximum CV. So we'll give just like 100 as a maximum CV. So we zoom in on the plot a little bit. So yeah, that's decoys, and then targets are like this. And if you have a really good memory, this kind of maybe starts to look like decoys. So whoops, we haven't scored this yet. So let's go run an mProfit model and score this and see what mProfit can tell us about all these peaks that we have, which are, admittedly for, 35,000 peptides. Yep. No, there's no protein. We don't have protein level CVs. Yep. So refine, reintegrate. And we're gonna add, it's gotta calculate. Other questions? So what we're gonna do, I think this is we're basically gonna create the refined document, and I think we're not gonna have time to go through actually getting the reports. There are zipped reports. But so what our goal here is we're going to do a comparison, and Mina's going to help us with the statistical part of it. But we're going to do a comparison between just taking this document as it is, which is what happened in the Bruder paper, or in the Selevsek paper, and running it against our osmotic shock data, versus using these 8 runs to pick only things that have low CVs. So that's going to get rid of, things that are experiencing weird interferences, degrading peptides. It should get rid of a bunch of noise. So it's a cleanup experiment, and it's actually using a prior experiment to inform our next experiment. So we're not doing this on the osmotic shock data. We're not trying to go like, oh, let's get rid of transitions now. We do the cleanup on a first data set, and then we redo the experiment, which is statistically way better than trying to clean up data that you're trying to run your statistics on. So you really would like to lock down your experiment, run the experiment through, and then do the statistics. But we're going to do it 2 ways. One way where we just take the library as it is and run everything and see if our statistics can clean it up for us, versus run a prior experiment, refine, and then use that for our important experiment. So let's train the model. As soon as you get up here, just click train the model, because that also again takes time. So if we can get more precise data, then hopefully that will improve our statistics. And if our goal is to get precise data on a certain set of proteins, then, well, we know if we were willing to just narrow down to a few proteins, we could do all kinds of experiments on the digestion, to get really, really precise assays. Clinical researchers, they optimize every step of the way, and then write a full protocol, and even get, they have to get FDA approval and everything. So, but we're just going to go one little step in that direction. And this is what the McCoss lab is definitely focusing on, and that's I mean, our favorite clinical collaborator, Andy Hoofnagel, is the one who came up with Mike with this idea to have Lindsay do the calibration of the entire yeast proteome so that we could get what are called figures of merit on every peptide that we were going to analyze. And some of them degrade, some of them have a linear range, and some don't behave very well at all. Yeah.
Measured versus quantifiable.
Yeah.
Is that true? And then
yeah, at this point we're doing a repeatability experiment.
Yeah.
So like the CBTAC has this assay portal where they're actually building assays, and you can go and say, I want to measure this peptide, and it's like, okay, here's the assay for it, and it's gone through 5 levels of refinement. It's gone through linear so it's gone through a sort of a linear range experiment to prove that it's quantifiable in a linear, it has a dynamic range, it's quantifiable. They do repeatability, so they do this 5x5 experiments where they measure it 5 times on 5 different days, and there's all this pretty rigorous amount of stuff that you need to go through, and this is just taking one little piece from that world over here, and we're just saying this is a bit of a repeatability experiment. Can I measure this peptide repeatably and get the same answer? Well, I mean, then what Lindsay is doing is this whole thing where she's doing dilution series into another matrix, and they really are trying to do a refinement where they decide, hey, this is quantifiable. But we're just doing, is it repeatable? So and what I think we'll find when we do the statistics is that just that one experiment to improve the set of peptides that we use to measure our proteins as things that are, when they stay the same, we measure them the same. Like we reduce the variance. So anyway, here's our model. Retention time looks like a better predictor in this data set. Shape and library are still big. Coalition count is pretty good, and product mass error is actually pretty good in this one. But we have this lump here, so there's a lot of, this is a highly fractionated experiment. There's a bunch of things that we targeted. So last time we found almost everything we targeted. Here we targeted, maybe half of our data or more is really, looks very similar to the decoys. And there's a little bit of an optical illusion here because we don't put these bars on top of each other. So it looks like this distribution is shifted to the right, and it's really much less shifted to the right than it looks. But anyway, so that's good. So this is a great model, but it gives us some insight into, wow, we have a lot of peptides that are probably not, we can't measure whether their CVs are good or not. So let's call this you can call it whatever you want. I'm calling it Selevsek 2015 tutorial. Okay. And I'm going to apply that model. Again, needs to be applied to everything. Takes some time. Hopefully it won't take too much time. Yeah, if you had done any manual integration, you might want to override manual integration. If you wanted to. I mean, you don't have to, but it's up to you. But we have not done any manual integration. This is all just completely, and again, everything I'm doing here I did on the command line. So I'm walking you through the manual steps, but if you wanted to do this a lot, move to a desktop with a lot more power, and I would recommend, grabbing those scripts and doing things on the command line. I actually did these data sets last night on that big computer and my computer, and I can tell you that this takes about 20 minutes. The processing all this this replicate experiment takes about 20 minutes, and then processing the full data set, which is, I want around 20 runs, 24 runs maybe. No, that's the other one. I don't know. 18 runs. That takes 40 minutes. I would say when it's this big, I don't really see the point. I would want to get down to manual integration. I want to get down to you know, less than 1,000. I would say, or less than 1,000 peptides. It doesn't, you know. So you, but manual integration and manual checking of the, you know, if you're going to report things or you're going to come up with targets for your next level, I would say don't just, you know, do all the statistics and walk away from your data set. Use the statistics, come up with some interesting things, and then go double, triple check them, and maybe then do a validation experiment on PRM or SRM, or, you know, like, so, but yeah, when you're at this statistical level, I would use the statistics to identify things to look at in this file. And Skyline will allow you to look at them. You don't, but you don't have, and like, don't, but yeah, forget it. You got 100,000, well, that's 50,000 precursors. You're not going to look at all those. But Skyline allows you to spot check anything you want. And yeah, it might be informational to just go through like 5 proteins and just look at all the parts. So I all of a sudden, I don't know that everybody had this. I maybe was playing with it. Does everybody's graph change to look like mine or not? Okay, so probably we got to go back to properties and define a CV, the Q value cutoff of 0.01. Everybody got that? Maybe while we're here, I'll increase the font size a little bit and click OK. And so now here, if I right click, I also have, yeah, so it says targets at 1% FDR. Do people have that now? So when I'm looking at the targets about at 1% FDR, things look a lot better. You know, with medians and at least 2 detections, I'm already at 88% below. And what I actually used for the next experiment was I increased the number of detections up to 4. It's got to show up in at least half my replicates. And now I'm 90% below 20% FDR. That's pretty good. So most of my things that I can detect reliably are actually pretty stable CVs. But then, so now I'm going to do my refinement here, and I just right click and say remove above CV cutoff. And now I'm down to, well, it says 100% FDR, but what's that? Okay, who can explain to me why there's something over the 20% mark? Well, it's because I'm using median normalization, and the median changed. So, so it really is, we got rid of everything that was before, and now our median CV is 7.8%, so pretty good. One last thing, well, 2 last things before we would run this again. We would go edit, refine, remove duplicate peptides. Oh no, sorry, edit, refine, remove empty proteins. And now you'll notice I don't have any reversed. I don't know if I started with any reversed in this file. And I want to regenerate the decoys. There's still a decoy protein here, but it doesn't really, it just has a bunch of unmeasured stuff in it. So edit, refine, add decoy peptides, okay, and okay. So now I have a new file that is this refined file. Whoops, did it do it? Oh. here. It's going to take a long time because the decoys are expanded. So now it's going to show, it's going to try to show many, many thousands of things. Bummer. All right, so let me just explain. So we would then, we're not going to have time to do this. We would then take this file. This is what I did. I took this file and imported it, imported data into it, ran the mProfit model again, and exported the report. Let's take a look at these peptides, these proteins. So you can see that some proteins still have a fair number of peptides, so we could refine this even further. We could choose, you know, you could use edit, refine, advanced, and we could say, oh, we want to take only 3 proteins per peptides per protein, and that would, you know, that would refine us even further, and presumably we would get better CVs. Not that much. Okay, so then we can take this document with the refinement, and we take our original document, which is the way the experiment was done in Selevsek, import data into both of those, right? Unprofit model, export reports, and then that's what you're going to run MS Stats on after lunch. And unfortunately, we didn't quite get through all that, but I'm over time again, so any final questions? So after lunch, you're gonna come back and work on the statistics of doing that analysis of whether, if you use, right? So you might start with the pan-human. You're going to do, you know, human cell lysate. I'm going to start with the pan-human library. And so the question for you maybe is, should you run a replicate experiment to see which of the peptides in the pan-human library you can measure repeatably and reliably, or should you just throw your data at the pan-human library and let MS Stats solve the mystery of what's changing and what's not? And that's the question that we had, and that you're going to get some insight into with Mina. Any final questions before lunch? Okay. Come back after lunch, and you'll get to look at the reports that get exported out of Skyline for these data. All right, thanks.